Hi everyone, thanks for having us on this discussion session. In Data Science Nigeria, where we have a vision to raise 1 million AI talent in 10 years. We're coming once again, and I hope we are staying safe wherever we are. It's been 2 weeks lockdown in Nigeria, and we hope that the vaccine gets released and everything can go back to its normal state. So wherever you are, I hope you are staying safe. We hope. So, with Data Science Nigeria is a non-profit driven by a vision to build a world-class artificial intelligence knowledge, research, and innovation ecosystem that delivers high-impact research, business use application, locally relevant artificial first startups, which we hope to increase employability and drive for social good use cases. Here is our chief visionary, convener of Data Science Nigeria, Dr. Bayo Adekombi. So you can look up our website for more information. With our vision, we can summarize this with the hashtag 1 million AI talent in 10 years. In the past 2 years, we've had some interesting and awesome key numbers. We have over 600,000 direct download of artificial intelligence for starter free ebook. We also have over 10,000 participated in the first ever intercampus machine learning competition. We have over 12,000 online participants in data science courses, from registration to at least one class. We have over 2,000 hours of free AI classes in data science and machine learning. We also have over 2,000 knowledge box, which is our 4 terabytes containing over 10,000 public AI learning videos from top AI schools, distributed free in 72 cities and campuses in Nigeria. We also have over 300 direct job placement, project participation, and internship. We have 48 research students being supported and mentored in high impact higher degree. In 30 cities, we introduce machine learning classes organized in 30 cities and reaching 5,000 students. Last year, we won 2 highest artificial intelligence award on the continent space at the Deep Learning in Daba, Kenya, the Matai Award, and also the second best research poster. Last year, we released the first AI book for primary and secondary school to be distributed freely through a structured train-the-trainer program across the country. Title of the book is Artificial Intelligence and Beginners Python Programming, which was written by our chief visionary, Olubayo Adekombi. We had a recognition at the world's largest artificial intelligence hackathon, Tunisia 2019 as well. Of course, we are humbled to run the biggest AI learning program in Africa with 26 unique platforms face-to-face, online, offline. So about team deep divers. To my left is a Victor Ireponen, a deep learning engineer at Retina AI. And to my right is Diko Stanley, a software engineer at Retina AI as well. My humble self, ML engineer and research intern at Data Science Nigeria. Together we represented University of Lagos at the just concluded Umoja Hackathon, where we have over 15 AI plus campuses and other African university competing for the same prize with the same vision. In Nigeria, we have over 16 AI plus campuses, and Unilag is one of them. So what do we have on this webinar content? We have a brief introduction to Zindi, exploration of the Umoja Hackathon, how we approach the problem, the framework we used and why, how we went ahead to create a base model, use of the trained model, how we improved the model performance, how we made prediction, the submission on Zindi platform, and conclusion and summary. So about Zindi. Zindi is the first ever data science competition platform in Africa, which hope to merge data scientists in Africa with African companies to solve indigenous problems. So on Zindi Africa, we took part in the advanced level Umoja Hackathon, where we had the opportunity to choose among 3. The advanced level was to use deep learning to classify invertebrate to classify invertebrate animals. So how did we actually approach this challenge? We look at how we downloaded the data set into Google Drive, how we loaded the data set, how we built our base model with PyTorch. At some point, we used the trained model via FastAI. We compared performance, and we did some API parameter tuning. We improve on model performance and make prediction on Zindi. So since we know that this is actually a deep learning challenge, of course, there are many frameworks we could use. We have TensorFlow, we have Keras, PyTorch, MXNet, and many other. But we decided to go for FastAI. Reason being that we are restricted and constrained to 8 hours. The hackathon lasted for just 8 hours. So we needed a framework that could be very fast at training, efficient, and require less code to write. And FastAI is the best library for this because it's an high-level library, high-level API library. So much less code is required to write most common tasks. It is very fast, easy to understand, and if at all we get stuck, we can easily check the documentation, which is also written in code. It also requires less debugging. So we went for FastAI due to the time and the performance of FastAI. Though we created our base model with PyTorch, because FastAI is built on top of PyTorch, we decided to remain in the circle to quickly build a base model with PyTorch. And before we went ahead to use our pre-trained model. So right now, it's time for us to just quickly look at our code and Colab link on Colab. So Victor, can you please run us through?
Thank you very much, Okpeyemi. So I'm Victor Repono, and then I'll be sharing my screen in a bit. Just 1 second. Can you see my screen come up now?
Yes, Victor.
All right. So I'll be taking you guys through the Colab notebook, the initial process of hosting or starting your machine learning competition, importing the required libraries, loading your data to FastAI, some exploratory analysis, and also visualizing like batches of the data set. I'll also be giving you guys some what not, do's and don'ts, a few tips here and there, which we employed in training our model. It's a discussion session anyway. So the first thing you do in a machine learning competition, if you are using Google Colab environment, is to mount your drive on Colab. So this line of code here imports the drive, and then we mount our drive in our Colab environment. Then the next thing you want to do is to specify the path to your working directory. Now, mounting your drive is not enough. You need to specify the path where your data is. So we specify that here, and then we are using os.chdir to change our location to that working directory. So we've done that here already. So that is what these two codes explain. We'll be releasing the notebook after this session. Then we also want to use or to reload and matplotlib inline. These are Jupyter Notebook functions. So auto reload ensures that each cell auto reloads on its own automatically. Then matplotlib inline ensures that our plots, when we try to do visualizations, it ensures that the visualizations are shown inside the notebook and not outside the notebook. So take note of that. Then we also want to be installing pre-trained models because we use pre-trained models. That was how we were able to get that high accuracy. Then judging by we had just 8 hours to train our model and make predictions, we had to go for the easiest, the quickest library out there, as Opeyemi said in his earlier presentation. So we use Fast AI library. Then we'll be importing that here. So we'll be importing the vision module. We're importing everything from the vision module. Also from callbacks, early stopping, learning rate scheduler, we'll be importing everything from callbacks too. Then from metrics, we want to import our error rates so as to evaluate our models. Then also from Pew, Python imaging library, we'll be importing image to read in the images and do some basic computer vision operations and to visualize some images. That is what this Pew library is used for. Then we'll also be using Shuffle from sklearn.utils. We'll be importing that. We'll also be importing Shuffle from Random. So this is to ensure that our model does not memorize the order in which the images come. So we want to shuffle the data set. So while that is done, the next thing you want to do is to download your data from Drive. So briefly, I just want to take us through in this page. So when you want to do a machine learning competition, so this is the page. This was the hackathon page. We did that on the 21st of March. So when you want to start an hackathon, it's good practice to read the description. It's good practice. Then also to go through the data at first. So in our data set, you can see that there are about 3,000 images in the train set, and there are about 1,400 plus images in the test set, and a total of 137 different classes. So you can see this was the challenge we were faced against. Then something else I want machine learning enthusiasts, people that are just coming up, to take note of is the evaluation metric. So always take note of the evaluation metric in any competition. Make sure you understand it and you optimize for that. So in this competition, the evaluation metric we were up against was the log loss. So while training, we have to make sure we optimized for this evaluation metric. So while that is done, the next thing you want to do is to download your data sets. And now there are several ways to download your data sets from a machine learning competition website like Zindi or Colab. You could either download your data set to your local machine first, then upload to Colab environment. That will take time. We had just 8 hours to do our competition. So rather than downloading our data set to our computer, then uploading to Colab, we used a Google Chrome widget called curlwget. So it can be downloaded from your Chrome extension office. So I'll just show you guys how it is used. So in order to use this widget, you just go to your data, then you try to download your data first. Then you won't let your data download. Yeah, so save data location, then you cancel it immediately, you start downloading. Then as you start downloading it, as you've canceled it, the widget has already taken note of the URL to get your data set. All you have to do is just to come and copy it and paste it in your notebook. So this is it, right? So we said it, yeah, for the train, we did the same thing for the two. So downloaded his data set already, show you what it's going to look like. It shouldn't. So this is the outcome. Okay, so this is how I think there is something wrong with the network. Okay, because I need to reload the page, but we won't bother about that. But this is how you download the data set. This is how we download the data set. So As soon as you've gotten your data set, the next thing you want to do is to unzip it, because it's in zip format. So we use this bash command. The unzip is a bash command. After specifying the not function, the unzip is a bash command. So you unzip the train and you unzip the test. Then you want to get rid of zip files, because you don't want to have redundant information in your Colab environment. Then after getting rid of that, we create a root directory called data. mkdir is a function. It's also a bash command to create a directory. So you use mkdir to create a root directory called data. Then you move your train and your test set into the data directory, as you did here, these two lines. We also do the same thing for the sample submission. Now, this is FastAI's format. FastAI's format, you need to have a root directory, then you need to have your train in the folder, you need to have your test in the folder, and you also need to have the sample submission file in the folder. So as a proof of concept, in this line, we listed out the contents of the data root directory. So just as I explained in the cell above, we have our train, then we have our test here. And we also have our sample submission that we've copied. Then also to see the 137 classes, as I showed you earlier, these are the 137 classes. So we listed out the content in our train folder. So this is it here. 137 different classes of images. So these images within it. Yeah, 137 in number. So that is that about that. Then the next thing we did is to create a random seed. Now this is a hack or a tip I want us to take cognizance of, because in machine learning you need to ensure that your results are reproducible. So we had that at the back of our mind, so that such that you can run your notebook 20 times and you get that same result 20 times. So we created a seed for the notebook for all the variables, and we created a seed of 2020 to ensure that our notebook gives us constant output at every time we run the notebook. Then that's that about that. Then the next thing we want to do is you want to load your data to FastAI. Now FastAI has a path function. So you specify your root directory or your home data directory inside this path function. So that is what we did here. We pass it to a path variable. So this is FastAI's format. It's a FastAI thing. Then next thing you want to do is to specify your train, your test set using the FastAI's root directory. So path/train, path/test. So this is our path for the train and the test. We also do similar for the sample submission files. So these are stuff you should take cognizance of while training with FastAI. We had to go with the shortest possible method, being that we are just 8 hours. You know, training with Keras or PyTorch you need a longer logic to do that. But with FastAI, everything is easy. That's why it's called FastAI. Then the next thing we want to do is, next thing we did was we did image augmentation. Now actually we could actually train from here. We've already specified data in FastAI format, so you could just load your data and start training from here. But we wanted to guide against overfitting, so we did image augmentation with this get transformed function. This get transformed function is a FastAI thing. So it's more like you are trying to do several augmentations on the fly while you are training your data set. As your model is training the data set, as you are passing the data set through the model, the images are flipping up and down, they are flipping left and right. There are different variations of lighting, different image operation is going on in the image, so that the model is seeing different versions of a particular image. That way, it makes the model very robust. You get me? It makes the model very robust, and there are different transformations that we employed from the documentations I showed you. This is the documentation. So we use the do flip vertical. Then we also did a max rotate of 10 degrees. Then we did a max zoom of 1.1, a max lighting of 0.2, max wrap and p-affine. If you are familiar with OpenCV with Python, then you'll be familiar with map-affine functions and wrap functions. So these are basically image operations that we did to augment the images we have in our data bank. Then the next thing you want to do is to specify a size for your images. So in this competition, we specified the batch size of 224. But before we got to this 224, individually, we had already tried training with different batch sizes. different image sizes. You get, so we tried with 400, with 700, with 500, with 350, but we found out that the 224 image size gave us the best result. So we stuck to 224 image size. Then also we specified a batch size of 16. Your batch size could be any number basically. So batch size is the batch of images that goes through the model. That is what the batch size is in layman English. So, and it's advisable to specify your batch size in byte format. That is 8, 16, 32, 64, 128, and 256, and so on and so forth in byte format. So, so we specified a batch size of 16, being that we are using a collab environment and the nature of the data set. Then we loaded our data then we called the FastAI's image data bunch class. So this is the FastAI's class to load your data set, and you could load your data from folder, from CSV, from data frame, from whatever means available. So this image data bunch allows you to load your folder, load your data set from whatever means available. So for this competition, we use folder. So we loaded our data set from folder, being that we have already Zindi gave us our data sets in folder format. So you just create your train, your test, and then you load your folder and you specify your part. FastAI does this, makes it very easy for us to do that. So then when you call the .folder function in the image data bunch class, you have to specify your path. Now remember, we've already specified this part right here, our home directory. So you specify your home directory, then your data set transforms will be your transformations for your image augmentations, then your validation data percentage. So this is the amount of our data we want to use as our validation set. Then our size, remember we specified our image size here to be 224. This size here is synonymous with image size. Then our batch size, specified it as 16 already. Then we specify your train, you specify your set, your test rather, and then the number of workers. Now, as it's just a bit of note, this is a discussion session. I just want to let you guys on this tip. I've noticed over the competition, but based on my previous competition and experience with Zindi, I've noticed that Zindi usually gives is data in form of folder. Why Cargo? If you're familiar with Cargo gives when dealing with computer vision tasks, Cargo release data to competitors in form of CSV format. So Cargo will give you your data set in a CSV format and your images. Zindi won't give you a CSV format, they'll just give you your images. So you will know how to use, you will know which function. I'm talking about this image data bunch folder. You will know which function to call if you want to call from folder or from CSV. So that's that about that. Then you run that. Then the next thing to do is we want to visualize the classes. Now that the data has been loaded into a data object in FastAI, so if you do a data.classes rather, it prints out all the classes available in the data set. So yeah, a total of 137 classes here. And then yeah, as a proof of concept, because it's not enough to just start training, you need to visualize to see what it is the data set looks like. FastAI makes that easy for us. Rather than writing code with matplotlib or Seaborn to visualize the data set, writing lines and lines of logic, a data.showBatch in FastAI will print out the data set for you. So we specified we specified 3 rows and then a fixed size of 7 by 6, and then this is the output data set. So at this juncture, I want Stanley will be presenting a screen talking about how to build a base model. So Stanley, over to you now.
Hello guys, I'm Stanley Debo. So thanks, Victor. Let me just share my screen now. Okay, so I guess you can see my screen now.
Yeah, we can.
Still coming up.
So yeah, Victor has done a good job in explaining how we can load our model, or rather our data set for training. So there are 2 things we're going to do. So I'm going to talk about how we can build a model from scratch using convolutional neural network. So basically how it works is that we when we pass our data set, the convolutional structure is that we're going to build a feature extractor, which is the essence of convolution. So like its name, convolutional neural network. So the neural network itself is the multi-layer perception. So the convolution is what we are going to use to extract features. Then we're going to use the multi-layer perception to train the model itself. So for convolutional neural network, what it does now is that given an input image size, so in this case, remember that Victor told us already that the image size is 224 by 224. Then also, let's not forget the number of channels, which is 3. So when dealing with CNNs, convolutional neural networks, the channel in this case is represented as the depth. So it's important to know that. So at the end of the convolutional layer, we expect to have an image with reduced dimension and a large number of depth. So that depth is more like the number of features generated. So that's what we're going to build now. So first of all, we need to import our important modules like touch itself, the touch library, then import touch.nn. So this nn function, what it helps us with are functions pertaining to convolutional neural network. So things like the conv2d, the max put 2d. So all these are just functions that we can make use of. And this function is also going to use to pass our data sets to apply things like ReLU and the rest. So just to go straight to the point now, so with PyTorch, you can actually define your model structure using two methods. There's a sequential method and there's a class method. So in this case, we decided to use the class method, but whichever one works for you, it's fine. You can check it on their documentation. So first of all, how we're going to do it now here, even though I declared a lot of things here. So how it works is that, first of all, you pass your image into the convolutional layer. The convolutional layer, what it does is that it extracts the features by increasing the depth. So if you can see it here, we're increasing the depth from 3, which is number of channel, to 16, from 16 to 32. So that's the increase in depth. That's what the convolutional layer is going to help us do. And the max pooling layer, which you can see here, is what is going to help us reduce the special dimension. So for the convolutional layer now, the structure in which we did, which I'm going to explain, made sure that for each convolutional layer, the size of the image did not reduce, but the dimension increased. So now, let's go through the function itself. So the first value that is here, which is 3, is the input channel, or rather the input depth. The next value we have is the output depth. Then this here is the size of the filter we are making use of. Then we also have padding, and then there's also the stride function. So the stride function by default is set to 1. So that's why we didn't need to modify it, because we made use of 1. So we are just going to go through the formula now. So this is the formula to work with for both the pooling layer side and the convolutional layer side. So for the convolutional layer, it takes in your image dimension, which is your width times your height times your dimension. So now, what expect our output, which is W2, H2, and X and D2. So I'm just going to take these two as the same thing, since we're using image an image with the same width and the same height. So our W is equally the same thing with our H. So now to calculate it here, so if we have 224 by 224, so our width is 224. Then remember that we specified our filter here. If you can see it, our filter is size 3, which is here. So 224 minus 3 is 221. Then plus 2 multiplied by our padding. So here our padding is 1. So which is 2 plus filters, that's minus 3 plus 2, which is 1. So basically what is just is 224 minus 1, which is 223, divided by our stride. Remember, our stride is 1 by default, like I said. So we have 223 as the output here. So then once you add it to this one, you realize that we have exactly the same size of image that we got. So that's the same for both sides. While this is our number of filters. So remember, our number of filters is 16. So now what we'll be able to achieve is just an increase in the number of filters, but the width and height remain the same. This makes sense. I'll just show the diagram here. So this is how it works now. Remember, if you specify a filter size as this, what our stride helps us with is the change in our in the number of pixels that we move by. So here, so if you have something like this now, using a stride of 1, this filter would go through from here. So this is just one step from here to this place. So the next size will be from here to this place here. So that's what the stride helps us with. So using a stride of 1 is like the best one, because you don't need to worry too much about your filter fitting into the whole image width or height, because once it's 1, you always go through everything. But when you use stride of 2, you always have to be certain that it would fit properly into the image dimension. So that's it with stride. Then for the padding, padding is the main reason why we got back the same shape, which is 224 by 224. So what padding does is that it adds zeros to the image, original image size. So you can see this is the image size here. Padding adds zeros to it. So it's more like then us applying the conventional layer to an image with an extra dimension. So this is more like an image frame. Yeah. So that's what padding does. So when we do this now, we expect to have exactly the same image size. That's how the conventional layer works. So now we also have the max pooling layer. Like I said, the max pooling layer is what reduces the image dimension itself. So what it takes now are two values, which is your stride, or rather initially, sorry, this is your filter size and then your stride. So if you check the formula here, this is that for pooling layer. So your new dimension, which is W2 by H2 by D2, would then be your actual width or height, which is 224 by 224, minus your filter size. I remember I recall the filter size is 2, so that's 224 minus 2 is 222, and divided by the size of our the value of our stride, which will give us 111. So 111 plus 1 will give us 112. So basically, we can then see that our next image dimension after applying the pooling layer is 112 by 112. So, like I've said, the depth does not change. So the depth remains the same. So, in this case, we applied 1, 2, like 6. We applied exactly 6 conventional layers. Max pooling layer, we applied 2. I'll explain why we use this one, a different one, in a bit. Then for our linear layer now, I'm going to talk about it too. So let's just go through how our model comes in. So if you have our model, our image, if you have our image as X coming into this architecture, the convolutional layer sees 224 by 224 by 3, which we all know. So it passes through our convolutional layer. Remember what I said, when it passes through our convolutional layer, we have 224 by 224 by 16 this time around, based on what we showed there. The next thing that we can do is to then apply batch normalization. So what is batch normalization? Batch normalization is this technique that helps improve our training speed, model stability, and increase performance of our model. So another thing, it helps us sort things like vanishing gradient descent. So that we apply our batch normalization. If you can see here, we define our batch normalization. So what you just need to pass into the batch normalization is the size of your depth, so which is 16 for that first one. So that's it here. After that, we then apply our activation function. So activation function is basically for non-linearity. So there are different types of activation functions. There's sigmoid, there's ReLU, there's tanh. But we decided to use ReLU because of its simple structure, its simple equation, and the fact that it performs well, makes our training faster too, and helps solve the vanishing gradient descent problem, unlike sigmoid. So now we've done this. Remember, at this point still, our model dimension is 224 by 224 by 3, or rather by 16, sorry. So then we then apply our pooling layer. So like I've said, our pooling layer is what reduces the image dimension. So if you apply this based on what I've said already, we know that our image dimension will then be 112 by 112 by 16. So if you apply the same procedure here, if you check, basically what I was just increasing is just the image depth, but it's the same procedure and reduction in the size that happens. So if you call now, this is 112 by 112. After applying our conventional layer, we'll have 32 here, up until when we get to our pooling layer. So if you have 112 minus 2, you have 110 divided by 2. That's 110 divided by 2. That's 56. Or let me just do the calculation. Okay, but because of time, I won't go through that again. Sorry. So if you have this, after applying our pooling layer, we'll have this dimension. If you do the calculation, we did already. So after this, it's the same procedure. We'll just keep doing. We'll keep reducing our dimension. We'll have 28 by 28. We'll have 14 by 14. We'll have 7 by 7. So this is where the issue comes in. This 7 by 7. So if you apply our pooling layer here, we have 7 minus 2. 7 minus 2 is 5. 5 divided by 2 won't work out. So we definitely have a negative, rather not negative value, a non-whole number. So a decimal value. So we have to change our pooling layer structure here. So that's why we have another pooling layer here, which is 3 by 2. So now this then specifies that our filter size is 3 and our stride is 2. So now if you try doing it now, that's 7 minus 3 is 4. 4 divided by 2 is 2 plus 1. We have 3 here. So that's why our new image dimension is 3 by 3. Then also, let's not forget the fact that our convolutional layer has increased our depth from 256 to 512. So now we have this. This is quite small enough and it makes more sense. We've reduced the image dimensions, gained a lot of features. So what's next is then pass it into our multilayer perception. So our multilayer perception receives a linear, an image with a linear dimension. So basically what we just need to do now is to flatten our image. So in order to flatten our image, what we need to do is to multiply all our dimensions together and just have just a single value. So now in order to do that, we just multiply the dimension here, which is 512 by times 3 times 3. So now the essence of this minus 1 in this view function is very, very important. And what makes it unique is the fact that we want our image to be flattened in a way that we'll have this as our number of columns, but our number of rows is what is going to be user defined. So remember, when Victor said was explaining how we load our images, we specified a batch size of 16. So any other person can decide to use other batch sizes like 32, like 64. So we do not know the batch size the user is going to declare. So we just put -1. So -1 just handles the remaining dimensions. So the point is just that we want to have this as our number of columns. Then our number of rows would be the remaining dimensions left. So in this case, since we use 16 batches, here is going to be 16. So that's how the view works. So now another thing then we get applied now is using dropout. So dropout layer, what it does is that it gives nodes with high weights, values of zeros during certain particular epochs. So in order to reduce overfitting is almost linear, is directly proportional with the size of the weight. So if a particular parameter has large weights, it's very, very likely for it to overfit. So the whole point is that we make those nodes have values of zeros so that they are skips during training, so that other weaker nodes can train during that procedure, so that there will be a balance. So that really helps in solving overfitting as a problem. So we apply our dropout layer, then we pass it through our first linear layer here, which was declared in this place. So we use it from the actual image flattened size to 200. Then we have our second one here, our second linear layer, which went from 200 to the number of classes that we have. So we have to specify it here. So this is number of classes, which is 137. So following the same procedure, we apply our linear layer, apply batch normalization, apply our activation function. Then we then do dropouts to reduce overfitting. Then we can then finally pass it through our final one that then gives us our output logic based on the number of images, or rather the number of classes that we have. So the next thing we need to specify is that we need to move our model to GPU. So definitely it's never advisable to train on CPU because you spend days training. This computation was 8 hours, and if you ever tried using CPU, we'll finish it the next week. So specifically we know what CUDA is, so we specify CUDA to be our GPU provider. So we move our model to GPU using CUDA. Then basically we can then do a model summary to see the model we built by running our model base. So this is exactly the structure we built. We applied the convolutional layer, applied our linear layer, applied batch normalization, and we can also print the number of parameters we have, which is this. So now for fast AIs, in order for us to load this our custom model that we built using PyTorch itself, we need to create a function, so a class rather, not function. So that class takes in the model we've built and also adds the GPU. So that's which is models.2. So we pass the two of them into different things, into two different objects in the class, and then return the model as a list or as an array, which is this. So that's what we load into our learner function. In order for us to load this into our learner function now, we need to specify the data set we want to train on, which is the first variable here. Then pass our model, which is this. So remember we specified this through this function. So we pass our model into this. Then we specify our optimization function. So we're using Adams optimizer. There are other ones we could have used. We would have used stochastic gradient descent, but Adams seems to be a better performer than stochastic gradient descent because it's more stable than gives better results. So another thing to then use now is our cross entropy loss function. So our loss function using process entropy. Then our metrics must say directory. So if I pass DSN, it will place DSN as the folder. So we're going to store our models in the models directly. So this automatically creates a directory for us. So now callbacks are going to add our callbacks like early stopping and save model callback function. So early stopping helps us to just explain what early stopping is. Early stopping makes sure that our model does not overfit. So how does it do it? So if you are training for like 10 epochs and our training loss keeps reducing while our validation loss increases at any point in the training epoch, we know that our model after it fits overfitting. So early stopping makes sure that it stops at that point in order to avoid overfitting. Then the second callback, which is save model callback. So save model callback, what it does is that it makes sure that the best model is saved. So like I've said, if we're training for 10 epochs now, and at the fifth epoch, we had the best model that was trained. Since it gets saved, even if you get to the 10th one, we can always load the fifth model since that was the best. So we load our callbacks into our function, and then now what we have to do is to start training. So for a start, it's good to use what do you call it? It's good to specify our learning rate. You have to specify our learning rate here. Then we use the function fit one cycle. So you pass the number of people you want here and the learning rates we're using. So here for the first one, the first training, we use this as our learning rate. So as you can see, this is the error rate which is specified in this place here. So remember, we said our metrics is error rate and accuracy, which you can see in this place. So this is the error rate, this is accuracy. Then another thing we did, which helps now, is to always load our best model after each epoch. So as you can see, but definitely in this case, our best model is the last one. But in some cases, it can be the previous one, it can be some other ones back. But it's just good to load the best model. After loading the best model, we trained on a lower learning rate now. So the accuracy increased quite alright, but still not the best. So after that, like we also said, is to load our best model. So at this point, OPM is going to tell us about training models, how we can build training model. Thanks.
Okay, thank you, Stanley. Thank you so much. I would like to share my screen now. Okay, so we've trained with a costume model. Right now, what we're thinking of at that point was just to use to use transfer learning, to use a pre-trained model. So what do we mean by pre-trained model? A pre-trained model is a model that was trained on large benchmark data set. In our case, we use a data set from ImageNet. So we need a pre-trained model at this point. So how does pre-trained model actually work? Now let's look at this architecture. We have the input layer, we have the pre-trained layer, we have the fully connected layer, which is the same thing as NanoNet, and we have the output. In our own case, our output will be 137 classes. So this is the pre-trained layer that we're talking about. So when we download the pre-trained model, what we are downloading is actually the trained weight in the pre-trained model, and we are downloading the architecture as well. So the pre-trained model we are actually using is the ResNet 50 that has been trained on images of class 1000, and the image is actually ImageNet. So we need to load the pre-trained model. Now when loading the pre-trained model, we need to specify the data, we need to specify the base architecture, and our base architecture in this case is ResNet 50, and also the metrics. Our metrics here is accuracy and error rate. So we need to specify the model directory. Now some callbacks. Thank you, Stanley. Stanley has done a wonderful job on the callbacks. The callbacks we'll be using is learning rate, minimum delta, and patience of 3. So loading the pre-trained model at first, it will download these trained weights and the architecture from the internet, and in this case it is 105 MB. So we specify our learning rate and fit the pre-trained model with 3 epoch. So our learning rate in this sense is 10 raised to power negative 2. So with this retrained model, we're able to achieve accuracy of 81%, over 81%. And if we look at this compared to our our base model, the accuracy was 87% and 83%. But at this point, we want to be very sure that our pre-trained model can actually perform better than our customized model or custom model. So we looked at how to load the best model. So we loaded the best model from our pre-trained model. We loaded the best model, then use a learning rate of 10 raised to power negative 3, then we'll fit it again on the model, and at this point we're already having 84% accuracy. So actually when we're doing the hackathon, we train more than 3 epoch. We train up to like 10 epoch, believing that our callbacks will actually take the best model for us. So we load the best model again, and at this point we are unfreezing the layers. So when we say we are unfreezing, this is the layer we are unfreezing. We are unfreezing the pre-trained layer, so that we want to see if we actually train the whole architecture now, whether we are going to improve on the accuracy or not. So if we look at this, we then slice through our learning rate. Why are we slicing through our learning rate? Because we want to keep increasing our learning rate as we train our model. So we train the model on 4 epoch here, though during the competition we train more than 4 epoch, and slicing through the learning rate and unfreezing the layers, we have accuracy of 85% and above. So from there we have enough confidence, we have positive confidence in the pre-trained model, and we continue on the pre-trained model. So I would like Victor to actually tell us how we went ahead and make a submission. So Victor.
Thank you very much, Yemi. So 1 second. I have to share my screen real quick. Can you see my screen now?
Yes, we can, Victor.
Okay. All right. So when after training our model, Stanley has talked about how we train our model, custom training. Then Okpeyemi has buttressed using our pre-trained model. Now we are about to make predictions. Then we tried to, in fast AI, the learn.getBreadth function is used to get your predictions. Then you're passing your model, your data, your test set inside the getBreadth function. So we tried to use this test breadth normally. Then we also tried TTA, which stands for test time augmentation. Then we discovered that we had a better accuracy using test time augmentation. So as of that, we commented this cell out and then use this line of code. So basically, how test time augmentation works is that while you are training your test set, you are augmenting your data set. Remember how I explained augmentation in data set preparation, meaning you are giving you are passing different variations to your data set, different variations of your data set through the model while you are making your predictions. So that's how test time augmentation works. And then we discovered that it gave us higher accuracy. It gave us a better accuracy than using the standard making prediction method in fast AI. So we employ this approach, and then it's a tip you could just keep in your bag when next you are doing your future competitions. You could just use it. Then to make after making our prediction, the next thing to do is to submit to Zindi. To do that, they've provided a sample submission file, which is how they want the submission file to look like. So after your machine learning competition, you are meant to submit to get your evaluation to see how your model is performing on the leaderboard. So then Zindi had already provided a sample submission file, which we have already passed in Fast AI. So we just read the CSV and store it inside a df sample variable. And .head shows us the first 5 rows of the variable. Now you notice I skipped this line. So this line is to get the names of all the classes in the test directory. So iter directory is a Python return function that it rates through the directory and gets the name. So we are storing the name inside this test names variable. Then right here we're printing out the shape of the prediction outputs. Then we're printing out the columns, the 137 columns in the prediction file, sample submission file. Then exactly, yeah, I remember myself and my colleagues we ran into an issue which you might run into in future if we don't address it now. So we discovered that fast AI makes its prediction in an alphabetical order. Meanwhile, the sample submission is not in alphabetical order. Like, let's take a look at this. You notice you have Terrasta capensis, Porifera, Astropecten irregularis, Pontoperius, and so on and so forth. I don't want to waste time pronouncing this. But if you take a look at this, you see that this is not in alphabetical order. But let's take a look at fast AI's classes. So if you notice, looking at this, when we printed out the classes, this is an alphabetical order from A's to B's to C's to E's to F's to H's. So this is an alphabetical order. And that is how fast AI made the prediction for us. So when we were submitting, Zindi was rejecting our submissions and we were wondering why, what's going on. Then one of us stumbled out, oh, it could actually be that fast AI is giving us the submission in alphabetical order. Meanwhile, Zindi expects it in this order. So what we did was very simple. We just wrote a logic to get the same order as submission. We replaced the columns and then we did a sub.head. And if you notice, our submission file is in the same format as the sample submission file. So then we called a pandas.to.csv. This is a .to.csv is a pandas function to convert your data frame into a CSV format, which can be submitted or uploaded to Zindi or to Kaggle or whatever computation medium. Then we specify our index to false. We don't want to have indexing in your submission files because your submission file has already created that for you. So this was how we did our prediction and we created our submission file. So we just went to Zindi and then we made our submission on this. Then I'll be calling on Stanley to talk about assembling, improving on model performance. So Stanley, take it away.
Okay, yeah, thanks, Victor. So let me just share my screen. Okay, I assume you can see my screen now.
Yes, we can.
Yeah, it's coming up.
Okay, you can. So yeah, I'm going to talk about how we can improve our model. So already we can get higher accuracies based on what's we've already gotten by building just a single model. But this is a competition definitely, and we have to find better ways of how we can improve our models in order to keep pacing on the leaderboard. So there are many ways you can improve our model. We could use stacking. So stacking of models. So yeah, basically, I'm just going to explain each of these processes and the ones we could use, the reasons why we could use them or not. So for stacking now, you know what stacking is. So stacking is basically just means building different models and then stacking them up to make our final prediction. So the issue with this is the fact that already training a single model takes time. Training multiple models takes time, but basically still a single model are training multiple times, so it still makes sense. But when we are stacking models, the time taken is quite a lot compared to that of a single model. So stacking is good, but for this short period of time, which was just 8 hours that we had, it was not really the best to use. So we discarded this method. So one now is pre-processing data with different parameters. So we already did how we can process our data. Victor explained data the pre-processing part, just like data augmentation, which helps a lot. So hyperparameter tuning too. PME spoke about hyperparameters. So basically, you can tune the learning rates, try different learning rate values in order to get it. The another one is to look for more data. Like we all said, the main key factor in neural networks are data set itself. So an increase in data sets improves model performance. What was stated directly on Zindi's side that we should make use of the data set that they provided for us. So this one too is rolled out. So another technique now, which is the one we use, which is assembling of models. So there are different types of assembly methods, but we try to use averaging, so which is finding the mean of different models we've gotten. So this is it. So it's one of machine learning's model for improving. So by averaging many different models, you can enhance signal and rules or rule out noise. So this was very, very crucial and important in the whole competition itself. So basically, what we just did is that we trained on different models and then found the average of their prediction, which was then our final prediction, which exactly follows this diagram here that we've seen. So I'll just walk you through the code that we made use of for achieving that. So basically, first of all, we need to import pandas. At this point, we're going to be working with CSV files. So pandas is the right thing for it. Then the next thing for us to use to import is our sci-fi. So sci-fi is where we're going to make use of our function, the function for finding the average. Then numpy definitely from them dealing with arrays in Python. So here you can see a list of the submission files we generated. So because of time, Opemi could not go through the whole training process we made use of. But these models achieved very high accuracies of more than 90%. So we made use of SC-ResNet 50, SC-ResNet 50, XC-ResNet 101. So all these from the pre-trained model library that Victor showed us initially. So then definitely we have to pass in our sample submission file. So the first thing to do is to remove the important part, which is actually the prediction. So if you can see is a sample.head, a .head representation of how our submission file looks like. It contains both the file and the predictions for each of the classes. So we do not need this first column here, but we need all rows in the next, every other column here. So in order for us to do that, we have to extract the important parts from this, which is this. So before that, first of all, we need to get the exact arrangement of the number of the columns here. So we store our column in this column variable. So next, we then extract all rows, which is represented by this column, all rows, and from the first column down to the last one, which is basically this, all the columns from this direction down to the last one. So basically, we want to just extract values. So we do that for all our submission files. So all we're left with are just values. So now next, what we do is to then use the start function, which is streaming. So I'll just explain what streaming is. Definitely, we could have just used the normal min method, which is just summing all the values and dividing by the length, which is the number of values. But there's something unique about this streaming, which makes it give better results than just finding the mean itself. So I'll just show it here. So if you look at this plot now, imagine we have our predictions now. So what streaming does is that it first plots it, not like it plots it basically, but this is just a representation, like physical representation of how it works. So if we have a plot of our prediction now, so basically we want to find the mean, and we all know the disadvantage of mean, which is the fact that it's affected by outliers. So what streaming helps us do is that it first gets this plot and then removes the outliers. So you specify the amount of outliers you want to remove, which I'll show us in the function itself, but it just removes the left and right outliers from it. So we'll just be left with the parts that were very set will give us the best value, which is around here. So now going back to the function itself, so you pass our cut out part, which is this, pass it into the function itself, and then specify the number of the percentage of the left and right side of the diagram, which I've just showed us, that we want to remove. So 0.2 means we want to remove 20% of it. So like this, if you say you want to remove 20% of the data set from both the left and the right side, so that's what happens. So it does that, emulates outliers, and then finds the mean. So from that, you can then use that, the results, which is basically the trained mean, to then get our new submission file. So basically what's just happening here is us fixing back the file column and the IDs, and then iterating through the columns and putting the mean values. So we then get back our normal submission format with the trim mean as the values here. So we can then do that and then submit and then get our results here. So okay, this is just a mistake. So that's just how it works. I think I will need to show us how we can submit this on Zindi. So yeah, so these are submission file here. I'll just run through it before we submit it. So, click submission. and average. So after doing this, we can do ls. We will see that our average value is then part of our it's part of our file here. So you can then go here. We expect to see it in the collab directory. Um, so average only that's Africa. Then yeah. So this the hackathon here. This particular hackathon submission. What's the size? So that's this time. Okay. Still downloading 4 MB. So while it's downloading, okay. So you can then sum the average. Mm, I don't know why it's taking too much time to. Okay, it's taking quite a lot. So.
Sorry, sir. Okay.
Okay, um, probably I'll show this at the end. So for now, let's open and present back.
Can you just show
So
the
I'll just stop
leader?
sharing for.
Can you just show the leaderboard over there? Okay.
Okay, okay,
Okay, you can go
yeah,
back to the submission back.
yeah.
Okay, so that's it, Abe. Okay, that was 4 days ago. So it's I think that is an
Let me
internal
see
problem
if
from Zindi right now because the hackathon has actually closed.
oh it could be actually or is it the size? Okay, it could actually.
Yeah,
But in order not to waste our time,
yeah.
we get an accuracy. You can see it here, the value here, which is average. So we have 0.248, which was the third position um, leaderboard here. Yeah, so that got us our results. Yeah. So up to your opinion yet.
Yeah, thank you so much, Stanley. Right now, I just want to share the last part of this discussion session. Um, we have so what comes to your mind when you want to do an hackathon or a competition on Kaggle or on Zindi? What should come to your mind is that complexity is never the best approach to handling challenges. Sometimes the best practice is to start with a simple model. Start simple before you start doing any augmentation or any parameter tuning at all. So you start simple so as to have a score to benchmark against. Because if you don't start simple and you start at the high peak, you don't have something to actually benchmark with. So when you start simple, then gradually progressing on it and improving on it. That is how hackathon actually works. And so another thing is you want to choose the best framework that suits the problem you have been given. So in our case, our constraint were time and the tasks were given. We noticed that, we discovered that the task that was given to us was this deep learning task, and the deep learning task requires enough time to train, and that is what Zinde has actually taken away from us, giving us 8 hours to train a good deep learning model. So we have to be very, very careful of the kind of framework we use. That was why we went for fast AI. So when you are doing when you are doing hackathon or competition, you want to choose your framework based on the project you are doing, and not just to showcase knowledge. Yeah, you might be good with TensorFlow, or you're good with another framework, or you're good with another complex framework. So you just have to choose the best framework that works best for that particular project, and not just to showcase your knowledge on a particular framework. So thank you so much for joining us for this session. We appreciate your time, and bye for now.
Yeah, bye.
All right.
All right, bye guys.